do this special portion of the lecture series. Since tayo lang naman, pwede po bang marap na lang po tayo dito para mas feeling close tayo sa isa at mas warm ang pagtanggap natin kay Dr. Danilo. Okay, so good morning again. So to formally open the lecture, may I call on Dean Rosemary Gutierrez for her welcome remarks, and then this is to be followed by the introduction of our guest lecturer today by Sir Ian Avalo.
Magandang umaga po sa ating lahat. I'd like to welcome our guests, co-faculty members, as well as our guest lecturer today, Dr. Danilo Romero, who is from the University of Maryland. For this academic year 2014-2015, Dr. Romero is our first guest lecturer, and we are indeed very delighted to be able to have such a distinguished scholar join us this morning to talk on the topic, Designing Novel Materials, One Layer at a Time, Prospects for Electronics and Optical Applications. We are particularly grateful and happy that he chose UP Baguio, and particularly the College of Science as the institution to visit here in Northern Luzon. Our College of Science lecture series serves as our venue to share and discuss research results of our very own faculty members from the college. It also serves as our extension arm of our college that regularly invites distinguished lecturers like Dr. Romero. Activities such as this are part of our continuing commitment to share our knowledge and expertise in the different fields of natural sciences and mathematics to the academic community of UP Baguio, as well as other academic institutions of Baguio City and nearby towns and provinces of Northern Luzon. I am sure we are looking forward to the interesting presentation of Dr. Romero, and may we have a fruitful and interesting exchange of ideas later after his talk. Let me take this opportunity to thank our CS Lecture Series Committee headed by Jericho Macani, who is not with us today because he is on official trip to UP Diliman, and his members like Professor Reginaldo, who took care of the preparations for this lecture of Dr. Romero. I'd also like to thank the faculty of our physics discipline headed by Dr. Ian Agulo, who made this morning's lecture of Dr. Romero possible. Again, our warm welcome to Dr. Romero, welcome to Baguio City, and welcome po sa UP Baguio.
So, ang role ko ngayon ay introduce yung ating speaker. But first of all, we're happy to have the guests from other universities such as St. Louis University, Sir Menandro. Then, of course, yung undergraduate students at faculty of College of Science. So, our lecturer for today is an accomplished physicist. Dr. Danilo B. Romero graduated BS in Electrical Engineering in 1981, and then in BS Physics in 1983, cum laude, at the National Institute of Physics, University of the Philippines, Diliman. So while graduate research assistant in the Department of Physics, University of Maryland, doing work on semiconductor physics, he obtained his PhD in 1989. From that time on until 2000, he moved from Maryland to the University of Florida, and then to Virginia Tech, and then to Ecole Polytechnique Federal de Lausanne, in Switzerland, doing postdoctoral research work as a visiting professor and as a senior research scientist. In 2001, he returned to the University of Maryland in the Department of Electrical and Computer Engineering as a senior research scientist. So para dun sa mga nagtataka kung anong gagawin ninyo after nyo graduate, yan yung mga isang posible nyo magiging magiging path. Okay? In his return to the University of Maryland, he was able to receive funding from the Department of Defense and from the National Institute of Standards and Technology, doing work on photocells, ultra-high memory storage devices, and optoelectronic devices. He has an exhaustive track record doing research on material synthesis, characterization and device fabrication, on fundamental condensed matter and materials physics, and on optical properties of materials and related devices. His current research interests are in the development of hybrid organic layered materials via atomic layer deposition technique, which is the topic of his talk today, transparent oxide and organic optoelectronics and photonics, and solar energy harvesting and storage. In 2008, he was awarded the Balik Scientist Grant short-term program with the National Institute of Physics as his host institution in order to give lectures series on organic, optoelectronics, and solar energy harvesting and storage technologies. Ladies and gentlemen, here to give us a talk on designing novel materials one layer at a time, prospects for electronics and optical applications. Let us all welcome from the Department of Electrical and Computer Engineering, University of Maryland, Dr. Danilo B. Romero.
Maraming salamat at magandang umaga sa inyong lahat. So since there's not a big audience and the laptop is over there, do you mind if I don't use the microphone and I'll just stand in front of the laptop? Okay, so it's really a great pleasure to give a talk and try to share with you the research that I've been doing and the interest that I have, and hopefully it will stimulate interest in, not necessarily on this type of activity, but stimulate interest for younger students to go to the fields of science and engineering. Because I think, especially with the upcoming ASEAN 2015, we need to be able to develop our human resource, to be able to compete with our neighboring ASEAN countries, right? Because there won't be any border, economically speaking, and so that's going to entail a lot of competition. And so I think we should be prepared for it. And I think one way of doing that is to go, into fields that will be required to be able to compete with when the borders, the economic borders open up by 2015. Okay? What I want to do is just really to give you an overview of this field, atomic layer deposition, as a technique to synthesize old materials and novel materials as well. Okay? So the things that I'm going to show you are, part of them are snapshots of work that we're doing in the lab, but mostly work that's done elsewhere. And just to give you, the current state of the art in this field. Okay, so let me begin with just an overview of the role of material science in general. So materials is always going to be the fuel that will drive technological innovations. You always have to start with materials, right? And an excellent example of that would be silicon. So are you all familiar with silicon? I'm sure you've heard about silicon. If not, I'm sure 100% that you've all used technologies based on this material. And silicon is very nice because it's abundant. You just go to the beach, it's there. That's why it's used a lot in the electronics industry. Now, And what's at the very beginning, material scientists really had to learn the properties of these materials, the electronic properties, not so much the optical properties because it's not a very good optical material. And the material science aspects, how to purify that, how to get rid of impurities, how to dope them to do something for very specific applications. Okay? Once you've learned the materials, so the next step in along this path towards technology is now you start engineering. You start to learn how to use these materials, like silicon in particular, to put them in devices, to put them, how do you engineer devices? Let's say, for example, here, I'm just illustrating two specific applications, right? On the bottom one is the very, very first transistor that's just made up of a discrete, actually that's not silicon, it's a germanium material. But then, as understanding of these materials evolved, they became more sophisticated, and I'll discuss this. You went into integrated circuits. You're able to put millions of circuits in one chip in this case. But it doesn't stop there. You want to go even higher densities. In other words, you want to miniaturize these circuits a lot more. So you develop the technology, the understanding of the physics behind those technologies. Okay? And then you go to the ultimate limit of making nanowires. In other words, these are silicon materials that are nanometer, that are even finer than a strand of human hair, okay, to make devices out of them. The other example would be photovoltaic devices, solar cells, right? So again, here, right now, the current state of the art in this technology is 24-25%. And that is very close to the theoretical limit, which is about 30%. Okay? So that's as good as you can get. And physicists and engineers have learned where are the losses coming from? How can you optimize the operation of these devices? So that's all the things, that in fact, in a certain sense, that's what we're doing in the university. We go to a very small device level, okay? Understand how you optimize all of this. When you apply for funding for DOST, you have to emphasize to them that what we're doing at the university is just a device level understanding. So it's totally different from, once you have optimized these devices, then you start to go to the real stuff that can be consumed by the public. So you want to be able to scale this to a larger, so you want to be able to make from small devices to solar panels like this. And there's a whole different types of problems in translating this from this part to this part. Okay, so that's, and it's the same thing here. You know how to make silicon nanowires, and you know how to make integrated circuits. But then it's a whole different problem that's that you'll encounter when you want to develop consumer electronics like the iPhones, like the Bio that I have, or even supercomputers. Okay? Now, and that's just based on one material, silicon. Okay? And silicon is really ubiquitous in our daily life. It covers everything from computing to harvesting power from the sun. Now, there are two ways of approaching this. One is what's called the top-down approach. Essentially, the top-down approach, you start with let's say the silicon bulk properties, then what you do is you develop the processes and the technologies, the techniques, the tools that will allow you to make smaller devices. And here I'm just illustrating the evolution of the technologies that are involved in manufacturing these integrated circuits that are used in consumer electronics. And there's a whole effort that's required to reach to this. Right now we're at this level where we can make devices that are of this size, 22 nanometers. Again, that's almost 1,000 times small, narrower than a strand of hair in this case. And the development continues. You always want to go to even smaller scales. Now, eventually, starting from that big chunk, the smaller ones, then you'll reach a limit where everything that you've learned up to this point will no longer apply, and then you start to do, and that's where the physics of the small world will enter in, and then you have to be able to make devices that will work using the principles of quantum mechanics in that case. So that's the top-down approach. The other approach, of course, is the bottoms-up approach. Here, it's the opposite. Instead of starting with a big chunk of material, you start with molecules, and you use molecules to build materials. Okay, and here the big players are chemists. Chemistry is a very important tool in controlling the growth of materials from the molecular level. So there's a lot of catalytic chemistry, molecular growth chemistry, self-assembly, and even atomic manipulation. I'm just illustrating a few examples here. For example, this one, this is, of course, this is not scalable manufacturing because you're using, I don't know if you've heard about a scanning tunneling microscope. Okay? Scanning tunneling, here, it's a special microscope that allows you to manipulate at the atomic levels. Okay? So here, this is a device that was demonstrated at IBM, where they manipulated the carbon monoxide molecules to form this device structure that performs a logic and gate operation. Okay? And you do that by just really working with an STM. The other one that's more mundane is self-assembly. Okay, so here's an illustration of assembled system of lead selenide and magnetite, Fe2O3, okay, to form what's called a metamaterial nanocrystal. Metamaterial, again, is a buzzword for designing materials that responds to light in a predetermined way. Okay? Now, and then this one, it's called molecular beam epitaxy, whereby you use molecular beams of, let's say, gallium arsenide or aluminum gallium arsenide to produce devices. In this case, what's called a Bragg reflector. Okay? And here we do have this, I think at NIP, right? The National Institute of Physics at the University at UP in Diliman. We have this capability. Now, and this the other example also of a bottom-up approach is atomic layer deposition. Okay, so that's what I'll be talking about. Okay, so now what's atomic layer deposition? So I'm just going to discuss this by showing you this movie. This is actually a movie that was provided to me by the company who sells the equipment that I'm using in the lab. The equipment that I'm using in the lab exactly looks like this. It's just that big. It's not very big. Okay? So it can be very big, but that's for if you want manufacturing. But I'm not doing manufacturing, I'm doing just research. So it's just a small scale. And it's something that we can actually, we don't need to buy it. We can build that here as well. We develop certain capabilities like programming and machining, which we need a very good machine shop to be able to build things. So I think that's one of the things that we should have here. Very good machine shop, very good electronic shop. Okay, that will, and then the know-how to be able to control experiments like programming, LabVIEW or things like this. So those are the things that we'll need to have. But let me show what is an ALD. ALD stands for atomic layer deposition, and start that. And what it is really is it's a sequential introduction of molecular gases into this reaction chamber. Okay, so in this case, let me just pause it. Pause it. Okay, at any rate, you can pause it. So you start with you start pulsing this. Usually you've got to have two gases that you introduce into the chamber, and then once you this one I want to do that. So, and these are called precursors. One of the precursors is the precursor that's for the material that you're interested with. The other one is an oxidant. And the way it works is the following. Okay? So in this case, this is illustrating how you deposit aluminum oxide in using an atomic layer deposition. So you start with what's called the trimethyl aluminum. That's the precursor for depositing aluminum oxide. So what you do is you basically that chamber that I showed you, you just pulse a certain amount of gas of this trimethyl aluminum into the chamber, and then then the TMA molecules will start covering the surface that you want to cover. In this case, it's the cover of, let's say, a silicon surface that's terminated with OH molecules. Okay? So you start doing that. And then once you do that, so it starts covering the, oops. So once you do that, it starts covering the entire surface. Now, the key to the atomic layer deposition is that once the entire surface is covered with this molecule, reaction stops. In other words, if you and it has something to do with the ligands that are included in that, in that precursor. Okay? Once you form the entire surface, no matter how much of these precursors you put, they don't react anymore. So the reaction stops. Okay? And so now you have this layer of, in this case, TMA molecules covering your entire surface. So what do you do? The next thing that you'll do is to pulse what's called the oxidant. In this case, the oxidant is just water. What the water does is to get rid of these ligands. Okay? It now exposes again the surface for the subsequent deposition of the atomic layers. So that self-limiting reaction is the one that's responsible for giving you the capability to control this on the atomic scale. Okay? So that's ALD in a nutshell. Okay? So let me just summarize the features of the ALD. So, self-limiting coverage. In other words, that's the one that really allows you to stop the reaction on one atomic level, one atomic layer. And that's very nice because it allows you to determine very precisely the thickness of the films that you're doing, because you just have a very well-defined layer of atoms that you're depositing on that. Okay. Now the other features is that right now atomic layer deposition has been in existence for almost 2 decades. So there's been a lot of research that's been developed to produce different chemicals to produce different types of materials. So there's a wide variety of reactors that's available that will allow you to deposit metals, oxides, semiconductors, and for various applications that you can think of almost. Okay? And the other important thing that is also key here is that you can build these materials at low temperature. Okay? Unlike, for example, most of the materials, let's say if you're going to make, I don't know, silicon oxide or aluminum oxide, normally you have to do that at very high temperature, above 400 C, above 500 C. You can do this at low temperatures. You can do this at 80 C or 100 C. Okay? And there are certain applications, let's say if you're interested with biological applications, this is going to be critical. Okay? Because, or organic materials. So low thermal budget is very important. The other thing that's not mentioned here is conformality. In other words, what the atomic layer deposition allows you to do is to cover any surface area that's exposed. Okay? It can be a flat surface area, it can be, like tiny buildings, or it can be sponges, it can be anything. It will coat that on the atomic level. And that's very, very critical for a lot of applications. So as I mentioned, there's a wealth of precursors that's already available, even commercially. Of course, I think here in the Philippines, I know that we have a very good tradition in chemistry. I only took one chemistry course at GUP, but I know that they are very good. So I think this is also one possible research for chemists is to be able to even just make synthesize already existing molecules, okay, for local consumptions, and then maybe eventually be able to design new molecules for newer applications. Okay? And what is it good for? These are just a list of potential applications that ALD is going to be very good at. So there's nanomaterials, nanolaminates, alloys, nanowires, nanodots. I really won't have